Water Resources Engineering Group. So although I'm the only person speaking here today, a number of colleagues working in areas in environment engineering. We do a lot of work related to water and wastewater treatment technologies, looking at the embodied energy within wastewater, life cycle analysis, and a major focus in our research group is basically how to harness wastewater as a renewable resource. And we're really seeing the paradigm shift of that happening. So for that, I've enclosed an article from Environmental Science and Technology that came out a few years ago. Dr. Jim Helsick, my colleague, and I were co-authors on this paper. And it's sort of it's an exciting paper, just trying to prime the pump and get people really thinking about what are the barriers in terms of recovering resources. Okay, so I'm gonna kind of breeze through the presentation in the interest of time. I know, there's more interesting things to look at in the lab, but I provided the presentation here. So if there's anything I'm kind of just flying over, you can kind of look at it more. And of course, you can ask me, your questions later on. Okay, so this is my research group, and like any professor, first thing you say is all the work is done by students. I actually don't do anything. I just try to get it out their way. So it's great when you have a phenomenal group of students who can make things happen. So we have wide engagement of undergraduate, graduate students in the laboratory. My research themes are sort of related to water and urban water cycles, and specifically focused on treatment. So there's work related to alternative supplies, water supplies, looking at rainwater harvesting, desalination, recovering wastewater as a renewable resource. We have moving on certain technologies to do that, and also then looking at the bigger picture of the urban water cycle. So wastewater, right? First thing I'm going to say, it's not anything pleasant. We all know that, but the fact is, it has carbon in it, it has nitrogen, it has phosphorus in it. We can either view those as a problem, or we can view those as an opportunity. And I think with 7 billion people on the planet making a lot of this every day, we really need to view this as an opportunity. We're going to get it right. So let me start with how we currently clean wastewater. We basically build wastewater treatment plants. There's a large expenditure of energy, chemicals, and labors. A lot of stuff goes into this, and we get this out, right? And this is a great accomplishment. In fact, most of the world still can't get this right. This is largely because of the Clean Water Act, created by the EPA, a lot of investment to make this happen. But along this way, we also generate a lot of air emissions, and we have a lot of sludge generated as a result of activated sludge treatment. In fact, when you do activated sludge, what you're doing is swapping pollutants for microbial mass for sludge. What do you do with that sludge? Well, I think a more sustainable way to manage wastewater, and the direction we should head in is we're still going to get clean water as a product out of this, but we're going to generate bioproducts, basically fertilizer, nutrients. In fact, we can even make bioplastic out of wastewater. And that has a lot of exciting potential in terms of finding a replacement for petroleum-derived plastic. And also energy. We need to look at wastewater treatment plant as an energy provider, a biorefinery. And then at the same time, we need to minimize the amount of resources that need to go into it to make this all happen. Right? So basically, a paradigm shift, looking at wastewater as a renewable energy, renewable resource, a number of sources, but out we're going to get water, energy, and nutrients out. And so we need to look at wastewater really as a feedstock for a biorefinery. And so what I'll be interested in asking, how can we make this happen? With the right technologies, that's fine, but really I think the regulatory framework needs to be in such a way to encourage that. So in terms of recovering water, we're I think doing a lot of it already, especially here in Florida, out west. A number of technologies can make that happen. Discussions on direct potable reuse. So I thought this Dilbert is excellent, right? And then the filter, you turn raw sewage into pure drinking water. Great, drink. Oh, whoops, that's the drinking water. So I think communicating science is very important also. And engaging your end user interface. You need to think about those things. Recovering nutrients. So that's the other big part. We know all the problems nutrients can cause when they get in the wrong place at the wrong time in terms of degrading water quality. But there's a lot of embedded energy that also goes into the mining of phosphorus and the production of ammonia, and those things are already in wastewater. So if we can harvest those, recover rather than remove, or some combinations of recovery and removal, I think overall the system will be a lot more sustainable. So looking at the energy potential of wastewater, right? The first one is look at the waste organic matter in the wastewater as reservoirs of energy. We've all been trained to look at COD as something bad, right? You have COD in the wastewater, get rid of it. Why? Because it causes degradation of water quality. But another way to look at it is COD can be your friend. The more COD, the more energy you can recover. So to do that, we need to really go back to the carbon cycle, to elementary school. My son's in 5th grade, they're looking at this right now. Somehow, by the time we grow up, we forget about the carbon cycle. That was just something we are today. Most Americans don't understand the carbon cycle. I think we need to go back to this. So there are a number of forms of carbon, and I like to kind of break it down into basically 3 major pools. We have organic carbon, biomass, that's you and I, biofuel, petroleum fuel, plants, animals, food waste, anything you can think of. Organic carbon in the middle. But you have 2 extreme forms of carbon, being methane and carbon dioxide. Methane is the most energetic form of carbon. It has the most electrons associated with it. You cannot get more energetically packed than methane. On the other side, carbon dioxide, the most energetically spent form of carbon. And in fact, the carbon just moves around planet Earth in a cycle. So we need to think about, well, how does nature spin the cycle around, and how can we insert the right technologies to manage carbon? Right? So they're saying that there is no waste problem, there's no energy problems. Really, it's a carbon mismanagement problem. So let's do that. So one of the things we can do is anaerobic digestion. We can turn waste organic matter into methane, and we're doing that already. Not enough. We need to find a way to do that more. And then once you have the methane, you can combust that, and then in the process you generate carbon dioxide. Now, now you get an accumulation of carbon dioxide. That's not good, but thankfully we have a mechanism known as photosynthesis. With the power of the sun, carbon is re-entered into the biosphere, and the cycle keeps going again. So this is where we insert technology such as algal biofuel to basically turn useless carbon into useful carbon. Right? So this whole issues of waste, energy, climate change, all this is really about thinking about carbon in a smart way. Won't go into calculations, but for a typical municipal wastewater, at about 500 milligrams per liter BOD, there's about 1.74 kilowatt per hour per cubic meter of energy embedded in that. So that's the US number. The more concentrated, the more energy in that. So the next question is, well, with that much energy, how much energy goes into wastewater treatment? Can wastewater treatment be energy neutral? Right? So looking at some literature values, let's say if we only harvest 25% of the energy that's built into the wastewater, we can't get 100%, so 25%. Let's say you use 0.3 kilowatt hours to treat the wastewater, we can potentially have a surplus. So we can meet our wastewater treatment goals and have energy left over. So that's kind of an interesting scenario where in the future wastewater treatment plants become sort of decentralized wastewater energy providers. So how do we get this energy from the wastewater? Our typical way of treating wastewater, many of you here are familiar with that, activated sludge process. Works very efficiently, but in the end you get a lot of sludge. Right? And the gist of this diagram is basically you start out with some waste matter, and we have different ways to channel the energy within the waste matter. When we start with an aerobic phase, activated sludge, we end up with about 60% of the energy built into the biomass of sludge. Right? Now we have basically 60% that we can do something with it. And if we anaerobically digest that, there's about a 10% loss. We can recover 90% of 60%. So you can see that if we do aerobic wastewater treatment and followed by anaerobic digestion of the sludge, we're only going to get 90% of that 60%. We're not going to get the full potential of the wastewater. So really what we need to do is directly treat wastewater with anaerobic processes, so they go after all of the energy that's within that process. And when you can recover that as methane, that's very compatible with natural gas. So there's a lot of potential to use that. So what are some technologies? This is something you'll see in the lab next door. It's something called anaerobic membrane bioreactor. Anaerobic processes have been around for a long time, but there are some fundamental barriers and challenges, and what we're trying to do is apply membrane biotechnology to make these processes better. Okay, and another thing we also look at in the lab is algae. There's a lot of interest in that now. Why? In the wastewater treatment plant, you have the requirement for oxygen, and algae provide oxygen. Microbes, aerobic microbes are respired to produce CO2. Guess what? Algae uses that. There's excess nutrients. We don't know what to do with that. We're trying to get rid of that within the wastewater treatment process. Algae can use that. And there's plenty of water also within wastewater that the algae can use. So there's great synergy between these two processes. So I envision wastewater treatment plants in the future actually become co-located with the algal biorefineries. So that means we need to redefine the mission of the wastewater treatment plant, not just to clean the wastewater, but also basically become biorefineries to grow algae for biofuel. Okay, so end up with this. Perhaps in the not too distant future, we'll develop point of use technologies like this. Totally off the grid. Okay, so with that, I don't know if there are any questions.